Okay. 30 to 20 years ago, I was strongly of the position that any presentation dealing with Charpy test had nothing to do in a fracture conference. That was 20, 30 years ago. Personally, I still have the same feeling. However, reality is something else. All the structural integrity procedures available allow the use of Charpy to estimate fracture toughness. The Eurocode 3 is based on Charpy estimating fracture toughness. So with this overwhelming fence that we can't climb over, at least we can try to lower it, or at least we can try to improve somehow the information from the Charpy specimen. Since it's anyway being used, let's see if we can improve it a little bit. So I will talk about sub-sized Charpy specimens, which are not so common for normal applications. Normally you just take a standard Charpy 10 by 10. But the sub-sized Charpy is a Charpy specimen where the thickness has been reduced. That's different from a miniature specimen where all dimensions are reduced. I'll just stick to this sub-sized specimen. The reason why I do that is that the steel industry is going to higher strength steels. They also go to lower thicknesses. And in many cases they are talking about thicknesses below 10 millimeters, 5 millimeters even. Normally you don't need to do Charpy test on those. But when you go up to ultra high strength steels with the yield strengths of 1000 or more, actually even those thin materials needs to be assessed based on fracture mechanics. And therefore you do need some evaluation. You need to get the Charpy value that can be used as estimate of fracture toughness, and then based on that do an analysis. And this is a work together with my colleague Päivi Karjalainen-Roikonen, typical Finnish name, and Pasi Suikkanen, another typical Finnish name, for SSAB, which is now owner of both Swedish and Finnish steel manufacturers. And they are focusing on these ultra high strength steels. So that's where the money is coming from, therefore this is what we're talking about. The problem with the sub-sized specimens is that it's not a simple fraction of just changing area fraction or something. Here's an example, Charpy energies for 5 by 10 specimens. And here's Charpy energies 10 by 10 specimens, standard specimens. Some norms, for instance the Norwegian norms and others, said that okay, for a 5 by 10 specimen you require 2/3 of the energy for a full-size specimen. Okay, that would provide a conservative estimate here, but here in the energy region usually of interest, that would be an unconservative estimate. Because in this region, the 5 by 10 has a tendency to produce even absolutely higher energies than a full-size specimen. Then we go here up to the upper shelf region, the reverse happens. So that the full-size specimen gives proportionally even higher energies than the small specimen. So a simple ratio correction is not correct and not sufficient. We need to do something else. The reason for this is very well shown by this old data set by McNichol from 1965 already, where he tested 15 millimeter, 10 millimeter, 5 millimeter, 2.5 millimeter, 1.25 millimeter thick specimens. And you see two trends here. First trend is that the transition goes down in temperature. Yes. Second trend is the upper shelf goes down with decreasing specimen thickness. And these are normalized by the area. So they should follow more or less the same line if it only would be a matter of correcting based on ratio. So okay, what can we do? Well, many years ago already, we looked at the transition temperature effect. We focused on the 28 or 27 joule transition temperature because there were a lot of data available. That translates to 35 joules per square centimeter. And looking at how that transition temperature changes with specimen thickness, we developed a simple equation for it, which even has some theoretical background there. I won't go into the, you can go to the original papers and look at what that is. We have also Welding Institute correction by towers that was basically practically identical. The difference here is that this was based on more data than towers had, and this also included data here with 15 millimeter and 20 millimeter specimens. So this correction goes also to actually thicker specimens. But it gives a very nice relation of how the transition temperature changes. The problem with this is that steel manufacturers says that, okay, yes, but then it means that we have to determine the transition temperature for the small specimens. And of course they just want to make tests at one temperature and say that, look, we are fulfilling the requirements. So that's not sufficient for them. Then we also have looked at the upper shelf behavior and developed a correction method for what happens with this upper shelf drop and why it happens. It happens because we're developing shear lips, and the energy for fracturing shear lips is only about half of the energy required for the flat fracture. So depending on specimen thickness, it starts here by 1-to-1 line for the proportional limit, and then a very small specimen, the effect of shear lip deformation is here, and then it becomes 100% shear lip essentially. At this point, this one transitions from flat fracture to shear fracture here, flat fracture to shear fracture here, flat fracture to shear fracture here, and even the 10 millimeter specimen, if I would draw that here, would have this transition up here. But this is for the upper shelf. So okay, we said, okay, would it be possible, instead of saying that this is for transition temperature and this is for upper shelf, let's use these for each individual test result. So you take one sub-size specimen, test it at a certain temperature, shift it according to this by temperature, adjust the energy according to this, because the amount of shear lips doesn't matter whether it's fully 100% upper shelf or not. And let's go back to this. This is the mechanical data, uncorrected, unadjusted. When you apply these two corrections to it, it looks like this. 15 millimeter, 10, 5, 2.5, and 1.25. The 1.25 starts to break down here because all of these equations were not developed to smaller thicknesses than 2.5 or 3. So I didn't expect it to work there. But amazingly well, it catches this region here for that as well. That was nice data with each point here is an individual data point. Then I took, as an example, a Swedish dataset by Malmberg from 1961, normal strength steel, 274 yield strength, and he compared full-size specimens and half-size specimens, so 5 millimeter specimens. Each point here now is the average of 20 tests. So this is the average of 20 tests, average 20 tests. When you do this correction here, you end up with this. And since these are average of 20 tests, much less scattered. But the adjustment works like a dream. Then to my employers, or not employers, but the ones who are paying for the stuff, the ones making the ultra high strength steels, This is a Finnish Optim 960 directly quenched steel, comparing 10 and 6 millimeter specimens with the adjustment. And here's Swedish, same strength, Weldox 960. They have now been renamed something else. 10 millimeter and 6 millimeter specimens, and again, considering that these are individual data points and there is much more scattering in these very high strength steels, it works quite well. So overall, this is a simple adjustment, works for any strength steel you have, and you don't need to determine a transition temperature. You just decide, okay, if my requirement is, let's say that 40 joules at minus 20, and I want to use a 5 millimeter specimen, I go to this here and say that, okay, if my requirement is minus 20, I have to do my test at minus 40 to make it equivalent to minus 20 for a full-size specimen. And then I just from here check what the requirement is for the small-size specimen. So if the requirement here is 60 joule per square centimeter, okay, then I require the same proportional value for the small specimen. It's only when I go to requirements above 100 where the actual difference starts to play. So in this region here, where we are actually usually fulfilling our requirements, a simple ratio correction is sufficient for the energy, but we do need this adjustment for the temperature as well. And that is something that the steel industry, they are pleased to say, okay, we can use this ratio correction. Oh, do we have to do a temperature adjustment as well? No, we don't want to do that. But if they want to have correct results, they have to do that. And we are on time for some questions if you have any. Thank you.